Continuing in Chapter 3, Section 5, we've looked at vertical asymptotes, domain, and holes. Now it's time to look at a horizontal asymptote to assist us in the ultimate objective of graphing rational functions. So a horizontal asymptote is a horizontal line. The equation of a horizontal line always begins with y equals. It's equal to y equals some number called b. The graph approaches and may touch or cross as x travels out to negative infinity and positive infinity. A rational function can have at most one horizontal asymptote. A reminder, vertical asymptotes, they're always of the form x equals and then some number, and we usually just use the lowercase letter a to represent that number. So vertical asymptotes are described with x equals, horizontal asymptotes are described with y equals. So let's let f be this rational function, where f of x is some polynomial divided by another polynomial, and it's kind of scary right here, but we'll ignore that, where p of x and q of x have no common factors, meaning we may have already factored and divided out and simplified. All right. So just graphically, a horizontal asymptote, let's go back to the main function that we looked at on the first page. When you look at the most simplest irrational function called the reciprocal function, okay, we did have a vertical asymptote at x equals 0, but the horizontal asymptote we can see at negative infinity to positive infinity, it appears that the graph is getting closer and closer to y values of 0 on both ends here. So we would say that we have a horizontal asymptote at y equals 0. Okay, so coming back here, how do we determine if the equation that we're working with has a horizontal asymptote, and what is it to assist us in graphing? Well, the graph of f, a function, has at most one horizontal asymptote determined by comparing the degrees of p and q. If n is less than m, then the graph of the function has the line y equals 0, or the x-axis, as a horizontal asymptote. Well, maybe we need to look at what n and m are. So going back up here to this kind of ugly equation, n is going to be the degree of the numerator, or simply put, the highest exponent in the numerator on the x variable, and m is the highest exponent in the denominator of the variable x. So if n is less than m, then the graph of f has the line y equals 0 as the horizontal asymptote. If the degrees are the same, then the graph of the function has the line y equals, we divide the coefficients, whatever numbers these are, a sub n and b sub m. So again, we divide these two numbers right here, and that becomes our horizontal asymptote. And the other comparison of the 2 degrees here is when n is greater than m, and if that's the case, then we say that the function f has no horizontal asymptote, that the graph may be coming down here and leaving up here, but it's not flat horizontally at both its ends like it is here. All right, so let's look at our reciprocal function right here, this equation. Let's find any horizontal asymptote. So I'm going, okay, horizontal asymptote's not vertical. So I can see that this numerator really could be replaced with 1 times x to the 0, because x to the 0 is just 1, so putting that in there isn't going to have any effect on changing this equation. The denominator is x to the first power. So n is 0. N represents the highest degree in the numerator on the variable x, and m is 1. It's the highest degree in the denominator. How do these numbers compare? Well, n is less than m. So let's come back up here to our 3 cases. N is less than m, so that means the graph of the function has a horizontal asymptote at y equals 0. So we have a horizontal asymptote at y equals 0. And that makes sense because we said graphically when we observed this graph that y equals 0 was the horizontal asymptote. We don't care about what's happening in the middle of the graph. It's the extreme left and the extreme right as to the behavior of the graph and what y values they're approaching. All right, so do we have a horizontal asymptote here? Well, we have the variable x, the degree in the numerator is 1, so n is 1, In the denominator, we have a degree of 1 also, so m is 1. So we compare n and m and we say that they're equal. So up here, that's case B. If n equals m, then the graph of the function does have a horizontal asymptote at y equals. And it says for us to compare the coefficients. So now we look in front of the x variable and we get 2. And we look in front of this x variable in the denominator and we get 1. So my horizontal asymptote is just y equals 2. So at the extreme left and extreme right of this graph, whatever this graph looks like, the y values are hovering near y equals 2. Okay, in C, I can see that n is 2 and m is 1. So we've got 2 and 1. So we have n greater than m, and when that's the case, we look at part C here, where n is greater than m. That means that the function has no horizontal asymptote. So I just respond and say none. Okay, let's look at D. N is 2 and m is 2. So n equals m. I do have a horizontal asymptote, and its equation will always be y equals, and we compare the 9 over the 3, the coefficients on those terms with the highest exponents. And 9 over 3 is just 3. So at the extreme left and the extreme right of this graph, whatever it looks like, the y values are getting closer to the horizontal asymptote of y equals 3. N is 1, m is 2. N is less than m, that's case A. So when we have bigger on bottom, we have y equals 0. When we have bigger on top, back here in this example C, 2 is bigger than 1, we have no horizontal asymptote. When we have the same, when the exponents are the same, then we divide the coefficients 2 and 1. All right, for our last example, n is 3, m is 2. Bigger on bottom because n is greater than m, and when we have bigger on bottom, we have none. Something that might help you with this horizontal asymptote is kind of this acronym that I've heard floating around out there. And so I think I'll share it with you because it might help you to kind of memorize what's going on here. Okay, there's this little silly saying. It's Bob yo, bot no, eats DC. I know that's weird. Bob yo, bot no, eats DC. And if we think about what these letters can represent, this is bigger on bottom for Bob, bigger on bottom, then y equals 0. Bigger on bottom, y equals 0. So let's come down here and look at some of those examples. In example A, we had bigger on bottom, 1 is bigger than 0. So our horizontal asymptote is y equals 0. Example E, bigger on bottom, 2 is bigger than 1. So Bob-yo, y equals 0. All right, let's look at bot-no. Bigger on top, no. That means none, no horizontal asymptote. Bigger on top, none. So let's look at that case where we had none. Bigger on top, yep, 2 is bigger than 1 when we compare the degrees, so we have no horizontal asymptote. It's what we call a slant asymptote. And that's beyond this course, that's for another course. Example F was none, so that must have been bigger on bottom, or excuse me, bigger on top, B-O-T. Bigger on top, 3 is bigger than 2, so we have none. All right, each DC is exponents are the same, divide the coefficients. So exponents are the same, divide the coefficients. We do have a horizontal asymptote, and the equation is y equals, and that's that a sub n divided by b sub m. So exponents are the same, divide the coefficients. Well, we did that here in example B and D. So exponents were the same, 1 and 1. So we looked in front of those variable x's and we divided the 2 and the 1, and we got a horizontal asymptote of 2. Exponents are the same here, 2 and 2. We divided the coefficients, 9 and 3, and we got a horizontal asymptote of y equals 3. So hopefully that little acronym might help you when you have to go to memorize how do I remember to get any horizontal asymptotes that a rational function might have. All right, now let's put all this together so that we can finally accomplish our objective, main objective of graphing rational functions. Here's the process in which we're going to do that. Blitzer might call this the 7-step process or the 7-step strategy. Okay, but what we're going to do is we're going to be given an equation. We're going to find the domain. We know how to do that. We're going to determine if any of the restricted x values of the domain give us vertical asymptotes or holes. We know how to do that. We're going to determine if there's a horizontal asymptote, which has the equation y equals. We'll use Bobbio-Botno eats DC for that. We already know how to determine x and y intercepts and get the ordered pairs, so we can plot those. And hopefully with all of this information, we can put it together and sketch a graph of that rational function. So we'll remember to graph the asymptotes as dashed lines. We'll plot the x and y intercepts if they do exist. We'll draw a hole at any x value that does not exist and is not a vertical asymptote. We'll plot additional points as needed. We'll follow the asymptote to finish the graph edge to edge. All right? So I'll pick up in the next video and we'll begin to sketch the graphs of these rational functions.